Namaste, Hamisha Khush Raho Bitiya. My name is JV'n Manisha Singh. Today I am teaching you Introduction to Rheological Properties. Now let's start the topic. What is rheological properties? It is a necessary to study properties of fluid, food products for designing and outlaying of transport system like piping and pumping layout. For the fluid food product, the design of transport system mainly depends on the type and description of the flow characteristics of the food product. Some of the properties are interdependent and some are dependent on the fluid food composition, and it is necessary to measure the dependent properties and we can predict its rheological properties. This is the graph in between the shear stress and shear rate. This is for the Newtonian fluids. This is for pseudoplastic fluids. This is for dilatant fluids. This curve, when we apply some stress on the plastic fluids, it will behave like a Newtonian fluids. Then pseudoplastic with yield stress. Then in terms of viscosity and shear rate, this curve is for dilatant, this curve is for Newtonian fluids, then pseudoplastic fluid, plastic fluid, pseudoplastic with yield stress. Most important dependent fluid food property is viscosity, that is resistance against flow, generally indicated by mu, that is dynamic viscosity, and kinematic viscosity. In food industries, mu is broadly used to describe a single parameter known as consistency. But this approach may lead to confusion in many cases due to non-Newtonian behavior of many food products. The rheological classification of food, the stress and rate of shear diagram indicate varieties of food products classified under different categories, which is considered to be non-Newtonian. Then this is the classification. The fluids can be classified into following categories depending on its response to the applied shear force, Newtonian and non-Newtonian. Time-independent flow of non-Newtonian fluids is called pseudoplastic shear thinning fluids and dilatant shear thickening flow behavior. And time-dependent flow of non-Newtonian foods is thixotropy, rheopactic, and plastic. Then Newtonian fluids. Newtonian fluids are the fluids which exhibit a linear increase in the shear stress with the rate of shear. These fluids exhibit a linear relationship between the shear stress and the rate of shear. The slope of viscosity is constant, therefore the viscosity of the Newtonian fluid is independent of the rate of shear. These fluids exhibit a pure viscous flow, that is, the product begins to flow with the slightest force and the rate of flow is proportional to the magnitude of the force applied. The examples of Newtonian fluids are milk, clear fruit juices, sucrose solution, most types of honey, corn syrup, etc. Then non-Newtonian fluids. A non-Newtonian fluid is broadly defined as one for which the relationship between shear stress and shear rate is not a constant. When the shear rate is varied, the shear stress does not vary in the same proportion. These fields exhibit either shear thinning or shear thickening behavior, and some exhibit a yield stress. The two most commonly used equations for characterizing non-Newtonian fluids are the power law model and Herschel-Bulky model for the fluids. There are several types of non-Newtonian flow behavior characterized by the way a fluid viscosity changes in response to the variation in shear rate. The most common non-Newtonian fluids are time-independent flows of non-Newtonian fluid, time-dependent flow of non-Newtonian foods. Time-independent flow of non-Newtonian foods are the foods whose viscosity is not influenced by the shear time at a constant shear rate show two distinct patterns of stress shear rate relationship, that is shear thinning and shear thickening. Pseudoplastic shear thinning fluids, this type of fluids will display a decreasing consistency with an increasing shear rate. Probably the most common of the non-Newtonian fluids, pseudoplastic, include emulsions and dispersions of many types. This type of flow behavior is sometimes called shear thinning, and protein concentrates, skim milk concentrate, milk ultrafiltration retentates, orange juices are the examples of the pseudoplastic fluid food products. Then dilatant shear thickening flow behavior. This type of fluid will display an increasing viscosity with increase in shear rate. And dilatancy is frequently observed in fluids containing high level of deflocculated solids such as candy, compounds, cooked cornstarch paste, certain honeys, types of honey, etc. Dilatancy is also referred to as shear thickening flow behavior. The shear stress shear rate curve is concave towards the stress axis and the value of n is the our law is negative. Time-dependent flow of non-Newtonian fluids. Certain non-Newtonian fluids show a time-dependent stress shear relationship which can be one of the following types. Thixotropy, when at a constant shear rate, the stress decreases over a period of time due to structure breakdown until eventually it reaches a steady value. The product is said to be thixotropic. Example is aged condensed milk, cream, ice cream mix, etc. Rheopactic, this is essentially the opposite of thixotropic behavior in which the fluid's viscosity increases with time as it is sheared at a constant rate. Rheopactic fluids are rarely encountered. Both thixotropic and rheopactic may occur in combination with any of the previously discussed flow behavior or only at certain shear rates. Plastic, this type of fluid will behave as a solid under static conditions. A certain amount of force must be applied to the fluid before any flow is induced. This force is called yield value. Tomato ketchup is a good example of this type of fluid. Its yield value will often make it refuse to pour from the bottle until the bottle is shaken or struck, allowing the ketchup to flow freely. Once the yield value is exceeded and flow begins, plastic fluids may display Newtonian, pseudoplastic, or dilatant flow characteristics. Important properties of fluid foods. Bounce, the resilience rate at which the sample returns to its original shape after partial compression. Then chewiness, it is the number of chews needed to masticate the sample to a state ready for swallowing. Coarseness, degree to which mass feels coarse in the mouth. Cohesiveness, degree to which the sample deforms before the rupturing during biting. Denseness, it is a compactness of cross section of the sample after complete biting. Then dryness, degree to which the sample feels dry in the mouth. Fracturability, force with which the sample shatters, breaks, it encompasses. Crispiness, crumbliness, crunchiness, and brittleness. Graininess is the degree to which a sample contains small grainy particles. Gumminess is the energy required to disintegrate a semi-solid food to a state ready to swallow. Hardness is the force required to deform the product to a given distortion. Generally, the distortion is between the tongue and palate. Heaviness is the weight of product perceived when first placed on the tongue. Moisture absorption is related to the sensory amount of saliva absorbed by the product in the mouth. Then moisture released, amount of wetness and juiciness from the product. Mouth coating is the type and degree of the coating in the mouth after mastication. And then roughness, it is the degree of abrasiveness of the product surface which is perceived by the tongue. Slipperiness, it is the degree to which the product slides over the tongue. Then smoothness, it represents the absence of any particle or lumps etc. in the product, just like chocolates. Then springiness and sponginess, degree to which the product returns to its original position, that is shape and size after partial compression without failure. Here compression is between the palate and the teeth. Uniformity, degree to which the sample is even throughout. Uniformity of bite, evenness of force applied on the food product while biting. Then uniformity of chew, the degree to which the chew characteristics of the product are even throughout the mastication. Viscosity, force required to draw a liquid from the spoon over to the tongue. Wetness is the amount of moisture perceived on the product surface. Hope you all are satisfied with this session. This session is powered by Digital version 2.0 Jayoti Vidyapeeth Women's University, Jaipur. If you have any query, please mention it in a comment box and I will resolve them whenever we have a live session. And thank you so much for watching this video.